Thank you, and I'd like to start by thanking the organizers for the opportunity to both make my first visit to BIMSA and also to speak at this conference. So in the spirit of Mark Spradlin's talk yesterday, this is going to be a review talk, but a little bit different from his. It's going to focus more on aspects connected to experiment and observation than to pure theory. In fact, we're going to look at frontiers of observation from the very, very small, which we probe at Hadron Colliders, currently the LHC, and beyond the scope of most of our lifetimes, perhaps at some future Hadron Collider, through human scales. I'm not really actually going to talk about any applications of human scales, although there will be some within the next year, assuming that Nimar Kani-Hamed ever bites up some of the things he's doing there, to observations that are just logarithmically shy of the edge of the universe in observations of binary black hole mergers. So the ultimate language for describing quantum phenomena is quantum field theory. And as I'll argue and as I'll show you, in some cases, it's even the best language for describing classical phenomena. And our goal throughout will be to predict observable quantities. So for my generation, and probably for younger generations, the quantum field theory is almost synonymous with path integrals. But there were other formulations of QFT before path integrals. And one of the interesting questions is whether there could be other useful formulations. And there have been hints of possible other formulations that have emerged in the last decade or so. Now, scattering amplitudes are a natural framework for both for doing explicit computations and also for investigating this question of frameworks other than path integrals, because you don't need path integrals, you don't need Lagrangians, Feynman rules, or the usual apparatus of textbook quantum field theory. In fact, in a sense, the whole subfield of scattering amplitudes, one can, if I can borrow a phrase from Lance Dixon, might call it quantum field theory without the quantum fields. So on the one hand, it gives us a toolkit and a philosophy for getting to observables efficiently. And on the other hand, over the course of the last couple of decades, it's become an interesting subject of study in its own right. And it has lots of connections to other fields. So it's connected to various frontier areas of mathematics. It's connected to areas of mathematical physics, integrability and string theory. As I've just mentioned, there's hints of new formulations of fundamental physics. And it's been a tool that's been used in explicit calculations in supergravity theories and also in Yang-Mills theories, whether QCD or the maximally supersymmetric form. And of course, its origins are in collider phenomenology, currently the LHC, but before that, the Tevatron. And the most recent applications, which I'll come to later, are to classical gravity. So at the very small frontier, the slow discovery of the Higgs boson about 13 years ago now completed our picture of the standard model. But we know, for a variety of reasons, dark matter being one of them, that there's physics beyond. And so we want to probe that physics. And our LHC for the foreseeable future will be our experimental instrument. Perhaps there will be a future E plus E minus collider to take over in Geneva. Perhaps there will be an E plus E minus collider built somewhere in China. In any event, the LHC is where we're at now. And in order to search for new physics, the next scale of interesting physics, then we already know that we're probably not going to find smoking guns. So we need to look for rare events. We need to look for events at tails of distributions. And in particular, we also need to be looking for small deviations from the predictions of the standard model. And in order to look for these rare events or small deviations, we have to understand known physics, the physics of the standard model, very precisely. So we need to know the relative rates of signals, of course, but more importantly, we need to know very precisely the rates of background processing, standard model. And these rates, of course, are given by integrals over squares of more basic quantities, the scattering amplitudes. So the amplitudes are, in fact, the basic building blocks that we have to calculate. So traditionally, I mean, going back more than a quarter century now, we would do that by computing lots and lots of Feynman diagrams, or more accurately, we would ask a graduate student or some young postdoc to compute lots and lots of Feynman diagrams, and they would confront the problem that there's a factorial growth in the number with the number of legs and number of loops, and there's huge cancellations. So there would be a certain amount of screaming and excitement as they force through all of these cancellations. And then one often finds that the results are amazingly simple. So I assume most people here have seen the so-called Park-Taylor amplitude before, usually written in terms of a one-line expression in terms of, in this case, the angle spinor products. What people may not know is that this is also an example of the violation of Arnold's theorem, because this form was actually not written down by Park and Taylor. It was written down by Mangano Park and Zhang Shu, who was at Tsinghua University, one of the inventors of the Chinese magic spinor helicity. So for those of you who don't actually know what spinor products are, then you can just think of these objects as being like square root of the Lorentz invariance for the purposes here. That's going to be good enough. So QCD is very important at the LHC because it's basically everywhere. It determines the structure of the proton, and it's a very essential part of the backgrounds that we have to predict. So just as a reminder, we have the proton made up out of 3 quarks, but as you probe it at shorter and shorter distances, then those quarks will generate what are essentially initial state gluons as well. So you have to evolve the initial states. That involves QCD. There's some short distance interaction, which for the bulk of the backgrounds also involves QCD. And finally, the outgoing partons will evolve and interact and shower, and that again involves QCD. So these are the dominant backgrounds to measurements and searches. And the experimental objects one sees, of course, are clusters of the hadrons that come out of the short distance partons. And so if one looks at pictures from Atlas, the vertical scale here is the energy projected onto the transverse plane, and the cylinder around the detector is unrolled here. So we have along the beam direction in logarithmic coordinates, and then around the detector in this direction here. And you'll see these clumps of particles, and with an appropriate algorithm, which is by now fairly well understood both theoretically and experimentally, you can classify these objects into jets. And if you were to make the mistake of looking down the beam axis, or take a transverse slice of the detector, this is from CMS, then again you'd see these clusters of hadrons, and of course there's tracks corresponding to them closer in the inner detector. So perturbative QCD is complicated because the strong coupling is not small. It's quite substantial compared, for example, to the electromagnetic coupling. And moreover, it runs quite quickly in the scales that are of interest, let's say 1 GeV to 1 TeV. So that means that the events are going to have lots of jets. You're going to generate lots of partons in the short distance interaction. Each jet in turn is going to, the radiation from in the outgoing state is going to create a lot of hadrons. And it also means that the higher order perturbative corrections are very important. So we can't just work at lowest order. That would correspond to tree amplitudes. In most theories, you'd start with one order. Maybe if you really need something precise, you'd go to another order. Here, because of the running, the first order is not even really quantitatively reliable. You have to go to next to leading order, where you now need to compute one loop contributions. And there's also a whole machinery you need for infrared cancellations, which I'm not going to talk about. And that was something that we overcame and kind of made industrial in the NLO revolution about 15 to 10 years ago. Now, I'm a resident of France, where the revolutionary tradition is actually quite bloody. When they have revolutions in France, they usually chop everyone's heads off and then start from scratch. This revolution was a peaceful one and a constructive one. And then beyond NLO, if you want to do precision physics, you have to go essentially to second order, and that's really where the frontier is. And many of the same ideas that were used in the NLO revolution, of course, have carried on, but there are new problems, and you have to develop new ideas in order to tackle them. So the basic ideas in scattering amplitudes is that everything, as much as possible, we compute from on-shell quantities. So you compute things, you can compute things from, whoops, hello, what is going on? Ah, there we go. I think I hit a bad button here. So we use only information from physical on-shell states, and that allows us to avoid the explosion in intermediate terms that would arise from Feynman diagrams because of the use of unphysical states. And of course, again, as I mentioned earlier, you don't actually need a Lagrangian. It's enough to start with the basic interaction amplitude, which in turn, you could just build from basic principles of Lorentz invariance. And it's kind of within the more general philosophy that in physical theories, you can calculate a wide variety of quantities, some of which are physical and some of which are not. The only things that you really have to calculate are physical observable quantities. Other things are your kind of choice. So the other key ingredient here is that properties of amplitudes become tools for doing calculations. So the kinematics gives us spinor variables. An integral decomposition comes from the fact that we have an underlying field theory, just the existence of an underlying field theory. Factorization gives us the on-shell BCFW recursion relations. And unitarity allows us to do loop calculations. And these are all physical properties of amplitudes that you turn into tools for doing calculations. So one can write down a master equation, and this, in principle, one can do at higher loops as well. It's not the way current higher loop calculations are done, but this is the basis for most of the one loop automated codes. So one can write down the amplitude as a sum over a certain set of basis integrals, and then in general theories, there will also be terms that have no integral functions and are just rational in the spinors. These are all Feynman integrals, and this is just this decomposition, and the set of integrals that enter just arise from the knowledge that there's a field theory and that we're working at one loop. And the key idea is that one wants to match the analytic structure on both sides of this master equation to then solve for the coefficients Cj. And ultimately, the Cj's are going to be given in terms of products of tree amplitudes, and then this assembling this expression will give us a loop amplitude. So the Yeah, I should also comment that the technology is such, which is unimaginable. In Feynman diagrams, you could actually do the entire calculation purely numerically, starting from the external states. The level of calculations, the level of cancellations in Feynman diagrams would be such that you would be left entirely with noise, and there would be no useful digits left. Yes. Yeah. Yes. Yes. So the right-hand side, these are known integrals. And so what you're going to be looking essentially is at certain discontinuities or generalizations of discontinuities. And so these are known integrals. They have known discontinuities. These terms do not have discontinuities. So if you're looking at some specific discontinuity, then you'll be isolating, for example, one coefficient over here. And then the discontinuity of the amplitude on physical grounds is going to be given by some product of tree amplitudes. So you're doing a one-loop calculation, you're re-expressing it in terms of lower, essentially a lower loop amplitude. So this kind of gives an idea of what was revolutionary about the whole approach, that if you go back to, for example, looking at Z plus jets, then going back to the 1980s, people did the first calculations of just Z production or W production. And then basically every decade, people would be able to add a single jet. And then starting in 2009, essentially every year to 18 months, we were able to add one more jet. And then at this point, the calculations were automated, and in principle, if you wanted to sink enough computer time into the numerical integrations, you could have kept on going. There are, in fact, measurements. I don't know about W plus, but certainly for pure jets, out to 8 or 9 jets. And just for old time's sake, this is an important background process to measurements of the top quark, and one can calculate at next to leading order the spectra of the 4 jets in the process. And again, just to come back to this question of numerically sensible or not, then the prediction at the leading order is this orange band, and you can see that it varies up and down by a factor of 2. So it's not really quantitative. And when you get to next to leading order, you're now down to kind of the 10 to 15%. So it's not a precise calculation yet, but it is at least a genuinely quantitative. So as I've already mentioned, if one wants to go to precision level, and obviously looking forward to the next 2 decades of LHC physics, even NNLO may not be enough. There's certainly some processes where you'll want to go to one order higher. But the basic idea is that the theoretical uncertainty should be a very small part of your uncertainty budget. So you have a lot of sources of experimental uncertainty. And in the predictions, you want the theoretical uncertainty to be much smaller so that you can make useful use of, the data as much as possible. And so here, the current frontier, or maybe a couple of years back, the current frontier was to compute 5 and higher point 2-loop amplitudes. And there are many young and hardworking people who have worked on that, some of whom are at least originally from China, although I don't believe from Beijing. One of the key tools, one of the key issues actually turns out to be the integrals. So there's an integration by parts that enters into the calculation of integrals. I'll come to that in a minute. But integration by parts also turns out to be a useful way of organizing unitarity, so that instead of doing that decomposition at the level of the integrals, you do it at the level of the integrands. And so at that point, you want to be able to separate out terms which integrate to 0. And here, a lot of effort has gone into results for 2-loop integrals. And there's also technologies involving finite fields and technologies that allow you to reconstruct analytic expressions for coefficients from numerical calculations, typically numerical calculations in finite fields, which you can do, of course, exactly as compared to in real or complex numbers. So as I say, the massless cases have kind of been computed, finished in the last few years, and all the helicities, all the different subprocesses, gluons and quarks, and I think people are starting to use this now for phenomenology. So we can get rid of the Feynman diagrams, but the Feynman integrals are with us forever. So you would originally imagine writing down some, in the traditional approach, some huge number of Feynman diagrams, and each diagram then has an integral. But these integrals have a large number of linear relations. And so one of the challenges is organizing and then calculating the integrals. So these have many, many linear relations, and you can find them using a technology known as integration by parts, on which enormous numbers of people have worked, and they're kind of maybe a small set of automated codes that most people rely on for explicit calculations. And in fact, they're kind of two codes, more recent codes out of China. This one is based in Beda, and this one is based in USTC in Hefei. So with these integration by parts, you typically can reduce systems of thousands of integrals to maybe a handful of what are known as basis or master integrals. And of course, some systems are larger. You might even have hundreds of thousands of integrals, reducing them to a few hundred master integrals. So what would otherwise be an intractable numerical problem becomes difficult, but still tractable. And then just let me finish this. And then of course, one has the problem of actually computing these integrals, and the method that seems to have taken over is one is known as differential equations, especially after the kind of reorganizational work of Johannes Henn. And the simplest of these, and those that are most relevant, are polylogs, and there's the symbol technology that has emerged. And it's also a place where more complicated mathematical objects, elliptic manifolds, and potentially hyperelliptic ones, and also for more complicated integrals, another appearance of Calabi-Yau manifolds in particle physics. Yes, there was a question. It doesn't. So for the most of these technologies, it doesn't really matter. Let's say for the more traditionally based IBP codes, I don't think it really makes that much difference which you choose. And other codes, for example, the need IBP codes, doesn't actually work in terms of loop momenta. It uses something called Bykov variables, which are essentially agnostic to the choice of routing of loop momenta. So the integrals also are a good hinge point from the very, very small to the very, very large, because they lie at the basis, and the challenges involved in computing them are kind of both one of the core challenges in frontier applications. So if it's a good hinge for us to go from looking at the very, very small all the way to the very, very large. And as probably most people know here, because you've all heard about the Big Bang, then the universe had a very violent origin. But maybe we should have called it something more exciting than just the Big Bang. In any event, the universe remains a very violent place. And much of that violence is associated with black holes. So let's imagine for a second a small black hole, let's say a 3 stellar mass black hole eating the Earth. I chose the size of black hole because it's roughly the same size as Paris. And of course, this is not something you really should try as an actual experiment. But if you were to do that, then this would release about 10 to the 40th joules, at least according to some online calculator I found. And within, I think it's of order a day or so, the Earth would be fully swallowed up. And just for comparison, the sun's luminosity is about 10 to the 26 watts, so about 4 orders of magnitude larger than the release over its entire lifetime. This would be released very, very quickly. So if we go a few orders of magnitude higher, then a supernova, for example, releases about 10 to the 46 joules, so 2 orders of magnitude more than the sun released over its lifetime, and that's just in a few seconds. And most of that energy is in neutrinos, which we can detect today. But its peak luminosity, the visible luminosity, is about 10 to the 36 watts, and that's roughly the same as the peak luminosity of a galaxy. That's why we can see supernova in distant galaxies and use supernovas as part of the distance ladder to try and estimate the expansion of the universe and how people discovered acceleration and so on and so forth. So if we look at essentially the visible night sky, then we find that it has another, we have to go up another 6 order of magnitude from a galaxy. Its peak luminosity is about 10 to the 42 watts. Well, if we look at the peak luminosity of a 30 pair of 30 solar mass black holes, so comparable to the very first event that was seen in 2015, then we find that it's over 7 orders of magnitude higher than the luminosity of the local supercluster. So in other words, it was for those brief tens of milliseconds that the event happened, it was by far the brightest thing in the sky. It completely overwhelmed the rest of the sky. So there you go. You're taking my next slide. And until about 10 years ago, all of this violence and all this energy was invisible. And that's precisely, as Kim Young pointed out, because it's all in gravitational radiation. You have no way to detect gravitational radiation. But the people at LIGO and then more recently Virgo and CAGRA are able to do that. And in 10 years and by now 4 actually observing runs. I should have updated this part of the slide. There are about 200 events. You can get information on them online. And the current run will end, I think, in about November. And most of these events are binary black hole mergers. There are a few neutron star mergers and a few mixed ones. So in a sense, these people got lucky because they were just, no one expected these binary black holes. They got lucky that there were a lot of them, so they actually had a lot of observing to do. And I'm sure you've seen this kind of batwing diagram of the binary black hole mergers, and then the kind of more smaller ones with that that have mixed behavior. So the science goals here are, first of all, of course, to determine the presence and distribution of heavy compact objects. And again, they've already discovered, LVK has already discovered this unexpected class of black holes. And there's every reason to expect that you open a new window onto the universe, and then as you collect more and more data, you'll find more surprises. So there are going to be more surprises in the decades to come. And of course, if I knew what they were, I'd write papers, but I'm just going to have to wait for the observations. Another aspect is that of neutron stars. So, and that literally has a connection to the Earth beneath our feet, because there's a question of how much neutron star mergers actually contribute to transferic element production, so all the heavy elements that we find on the Earth. And there's a long-standing problem of determining the equation of state, and that's something which observations, once the statistics get good enough, will be able to give us information. There could be precision strong field tests of Einstein gravity, and if one is very, very optimistic, there could even possibly be insights into quantum gravity. That, of course, depends on nature cooperating with it, but that's something one can hope for. Anyway, this is all very, very exciting, but what do theorists have to do with all this very, there's a huge amount of intricate technology, lasers and mirrors and cooling and mechanical damping. What do theorists have to do with this? So one thing one has to realize is that if you look at the noise level, then it's actually huge compared to the final signal. So notice here the scale is 10 to the minus 18. Here it's 3 orders of magnitude smaller. So after very sophisticated filtering and analysis, you go from these signals to something that is over here that still looks entirely like noise. And from that, you have to fish out the actual binary merger signal. And in order to do that, you have to have what are called theoretical templates. You have to predict the form of the wave train. And in order to do that, that's where you need theorists. Finally, once you've actually found an event, again, you have to know the precise dependence of this wave train on the parameters of the system, the two masses, the spin, inclination angles, and so on and so forth, in order to actually make measurements and extract information from the observations. So the basic setup is that we have two slowly inspiraling compact objects. Imagine these things being black holes. And they're slowly emitting gravitational radiation. This is still when their separation is much larger than their radii. So this is, you can treat in weak field perturbation theory. And eventually they get close to merger. And at this point, the fields are strong, and also the velocities are typically a significant fraction of the speed of light. And at that point, at the point of merger, you need to do this with the numerical relativity. And then finally, once the two black hole horizons actually merge, then the thing rings like a bell for a while. And that's something which, again, you can do using normal mode perturbation theory. And one of the challenges, one of the goals, is to try and push the weak field calculations as close as possible to matching with the last orbit and the region where you really have to be doing things numerically. And again, so these templates, you need both to fish the signal out of the noise and also then to do measurements. So when I give talks on doing perturbation theory for gravity, people say, well, you know, why don't you just do it numerically? We have computers, we have the theoretical framework, and you can do that. It's certainly very valuable to do cross-checking, but it's computationally incredibly expensive. I mean, each of these things, each of the templates is days, if not weeks, on a supercomputer cluster. And so if you want libraries of hundreds of thousands of templates, that's going to consume the entire computing budget of the planet. There are also subtleties that in if you go to the region where perturbation theory is very reliable, you have long wave trains, and the numerical calculation will accumulate errors over those long wave trains. And so you then have to invest even more numerical effort to get those down. So it's really a complementary tool. It's useful for doing cross-checks, but it cannot be the only tool that you use for doing calculations, for generating templates. So traditionally, of course, there's a small and very hardworking community of general relativists who do general relativity perturbatively. And about 20 years ago now, there are a pair of particle theorists, actually, Ira Rothstein and Walter Goldberger, who pointed out that you can use the ideas of effective field theory to take advantage of the separation of scales, because we have really three scales that are involved here. One is the size of the object, so if you like the Schwarzschild radius, and the other is the separation between the two, so the radius at which they're orbiting. And finally, there's a third scale, which is the actual scale of the gravitational radiation, which in this in-spiral phase is again going to be much longer than the separation between the two objects. So you can use the ideas of effective field theory to compute better, still within the context of general relativity. So then the idea came out to try and use scattering amplitudes. And in fact, that idea came from one of the leading general relativists who's worked on precisely the prediction of gravitational wave quantities. And so he's the one who said, well, this is a hard problem. Maybe all these scattering amplitude people should think about it. And so a whole group of people did. And I'm going to try and explain some of the key aspects that actually make this a reasonable thing to try and do. So at first glance, this seems like a very silly thing to do, because scattering amplitudes we're completely in the quantum regime. We're doing unbound scattering. That's the setup. That's the experimental setup at collider physics, where it started. So whereas the GR problem is, first of all, it's a classical problem, and then it's also a bound state problem. So these are two kind of seeming inconsistencies. So why might scattering amplitudes help? Well, first of all, there's the general philosophy. You calculate only what's needed for physical quantities. You don't have to employ auxiliary Hamiltonians or potentials, and you don't have, from the point of view of the infrared structure, you don't have to do ambiguous separation between conservative and radiation reaction. And there are technical advantages of that sort. But that's pretty weak motivation for doing such a hard program and developing a whole new set of applications. The real juice, if you like, and the real motivation, the real reason you think you can make kind of a revolutionary impact rather than kind of just an incremental one is what's known as the double copy. And that's the observation that amplitude calculations in gravity can be vastly simplified by the observation that in a certain sense, gravity is the square of Yang-Mills. And that's originally due, in fact, in string theory to Kawai, Llewellyn, and Tai, and later was developed by a variety of people. There's the BCJ relations, which are related, and there's also a formulation which is due to, among other people, Song He and Ellis Yuan. Song is at the ITP here at the Chinese Academy of Sciences in Beijing, and Ellis is in Hangzhou. So in a sense here, what we're doing is, of course, one is starting general relativity is essentially thinks in terms of geometry. It's invented by Einstein. So in the spirit of having thrown out Feynman diagrams, we're going to throw out general relativity. And we're going to turn for inspiration back to Feynman. So Feynman's view of gravity was that he looked at, he was, I think, really the first one to formulate gravitation as a spin-to field theory, ordinary field theory of spin-to objects subject to certain constraints. And in his very physics-driven way, then in his paper, he writes that we should review some of the experimental facts which a theorist would have to play with in constructing such a theory. It's also kind of a very idiosyncratic spelling of Venusian, but so be it. So, in fact, the vertices corresponding to the spin-to field theory would be written down by Bryce DeWitt, and they are pretty complicated. So you'd have 3-point vertices, 4-point vertices, and actually in gravitation you have n-point vertices. It's not like Yang-Mills, where even in the Feynman diagrammatic expression, you just have 3- and 4-point vertices. So here you have a large number of vertices, and they're actually pretty complicated. And it's even worse than what it seems, because there are these p symbols which instruct you to symmetrize over certain sets of permutations. So if you were really to write out all the independent terms, even this 3-point is not something that fits on a pair of lines. It would take half a page. And of course, this is on shell, and if you go, this is off shell, excuse me, and if you go to the double copy to the on-shell amplitudes, and you go to the simplest possible on-shell amplitudes, which are 3-point amplitudes, then you find a very different picture. So this is the 3-point version of the Park-Taylor amplitude. And you can do the same argumentation or same calculation in gravity. And there, at the 3-point level, you literally find that once you've stripped the coupling, the gravitational amplitude is the square of the Yang-Mills. So that enormously complicated thing on shell is basically just the square of the much simpler Yang-Mills vertex. So this is the field theory equivalent of the Kawai-Llewellyn-Tai expression, which relates closed string amplitudes, re-expresses closed string amplitudes as convolutions of open string amplitudes. And of course, like the KLT formula, it has a generalization to higher point amplitudes, where essentially the gravitational amplitude is written as a discrete convolution of Yang-Mills amplitudes. But the key takeaway here is that you can vastly simplify, if you need a gravitational amplitude, you can vastly simplify its calculation by organizing it in terms of Yang-Mills amplitudes. So we, of course, bring along the rest of our toolkit. We organize things in terms of gauge invariant amplitudes. We have recursion, we have unitarity, we have differential equations for the loop integrals. The loop integrals are different now because they involve, they necessarily involve massive legs as opposed to the more at least the initially interesting ones just being all massless. But the same technology can work. Maybe you find elliptic functions at lower loops than you would have in QCD, but there's a huge part of the toolkit that comes along. And for various historical reasons, there's strange names that are given in the GR community to just the ordinary relativistic perturbative expansion, which is just an expansion in powers of Newton's constant. One can also expand in the velocity, the relative velocity of the two inspiraling objects. And certainly in many cases in the far inspiral regime, the velocities are moderate. So that's a useful expansion. This is known as the post-Newtonian expansion, and it's the same kind of thing that's used in solar system tests of GR. And this is kind of where we know, and this is kind of where we would like to be, certainly preparation for the next generation of observatories and for LISA. So this activity has led to many different approaches and many different calculations, a large number of very energetic young people working in the field. And one of them, Fei Teng, or Fei Tong, I should say, is at Fudan University in Shanghai. And I think there's, well, Yutin is in Taipei. I don't know if there's any, and as is Shachen. I don't know if there's anyone else who's actually physically in China right now. In any event, I can't discuss all of these different approaches, but some of them have, in fact, led to concrete applications in predictions that are relevant to observation. So there's a formalism called the effective one-body formalism, which allows you to assemble kind of hints from many different calculations and puts in some guesswork as well, and then kind of feeds this into a machinery. But in any event, you can include the contributions that come from calculations by some of the scattering amplitude people, and then you see that as you go down to close to last orbits, you get very, very close to the numerical relativity prediction. So your ability to match on to numerical relativity towards the end of the in-spiral is greatly improved. And again, you see that here, this is with the inclusion of different relativistic orders. So the dots here are the NR prediction. And you can see that as you add in more and slightly different approximations, that you're improving the connection to numerical relativity. And numerical relativity, at least here within the uncertainties, is actually the truth. So you're getting very close to the truth. So let me very quickly go through one of the formalisms that, which is kind of the one that maybe makes the path from quantum field theory the smoothest. So we're going to be thinking about a scattering situation. So we're going to scatter two things. You can think of them as black holes or as massive point particles. And the transition to bound state predictions is, in fact, still one of the areas of active research. And they're, as usual at the frontier, there are puzzles and there are things that are understood and there are things that are not understood. So the basic idea is that one can start in the quantum theory and pick observables that are also relevant classically. We express them in terms of scattering amplitudes in the quantum theory. And then we understand how to take the classical limits. So you restore H bar, you rescale the couplings properly. You have to differentiate now between wave numbers and momenta. So momenta for massless particles, wave numbers for massive particles. And then you essentially turn the crank. I mean, you have to do some argumentation about different scales, but that you really just have to do once. And so examples would be, you have to, of course, you're not interested in plane waves. Here you have lumps of matter, so you build relativistic wave functions. And of course, for the lowest order in the size of the object, the details, the wave function ultimately drop out. They'd be important if you're starting to actually look, for example, at the inner structure of neutron stars. And then you can construct, for example, observables where you measure the momentum. That's just plugging in the momentum operator, and use the S matrix to rewrite the out state in terms of the in state. And that finally gives you a master equation. So if you're looking, for example, the change in momentum, there's going to be two terms, one of which involves a cut, and the other is just loop corrections at higher order. And you can go on and similarly do observables that involve, involve the propagation of radiation. So we imagine there's some scattering region, like the region where the binaries are spiraling and then and emitting gravitational radiation. And then very, very, very far away, because we're typically hundreds of megaparsecs, if not gigaparsecs, away from these events, the radiation propagates, and then we have some observer. Of course, the observer is not just a pair of eyes; it's some very sophisticated observatory like LIGO, and you can then build a radiation observable, and the waveform is just the leading large distance behavior of that observable. So again, it's just a few technical, well, one or two technical slides. So in our case, we can measure the Riemann tensor, or you can actually do it in terms of Newman-Penrose variables. And of course, at leading order, things simplify a little bit, so you get what looks like a messy equation, but basically it tells you to do a certain Fourier transform, after you've taken limits, it's a certain Fourier transform of a 5-point amplitude. So the waveform, in a sense, you can think of as just being a 5-point amplitude. You have the scattering of the two massive objects and the emission of one graviton. That's the key object which you have to compute. So, courtesy of a colleague who's actually at Penn State, Radu Roiban, then I think this thing is going to show you what an actual wave would be. So that's the metric, and as the wave is going through, there's two helicity states, plus and the cross, and you see the thing being distorted. So that's what the future is going to look like. We're going to have another generation of ground-based observatories. Well, I mean, they have not been funded yet, but I think the odds are good that at least one of them, the Einstein telescope in Europe or the Cosmic Explorer in the US, somewhat different philosophies. And again, presumably they will join up to increase the observing power by collaborating. And it's interesting, so far there's no corresponding terrestrial observatory proposed in China. There is also a space-based observatory, LISA, and there's correspondingly a Chinese proposal called, I think, Tiaji. And they have, I think, very much a similar philosophy, and there's some possibility the two collaborations may actually combine. So that brings me to my summary slide, and I've tried to give you a little bit of a picture of the powerful framework in computational technology, and both for purely quantum applications and also for classical observables, and at the two different distance frontiers. And one of the things I haven't really talked so much about, but has been key to the advancing in the field, is that one has sometimes new ideas about how to do calculations. They allow you to do calculations that were too hard before, and that allows you to observe new properties of the amplitudes, or new properties of the components of the amplitude, like the integrals, and that in turn gives rise to new ideas about how to do even harder calculations. And that kind of virtuous circle has been going on for 2 decades now, and I think it will still has time to run. And of course, there's hints, which I haven't really talked about, but just mentioned that there's new hints in related work that there could be other formulations of quantum field theory as well. So let me stop right here and just thank you for your attention.
Are there any questions?
You mentioned that the Young-Mills scattering amplitudes are related to gravitational ones. Is it well understood relations also can, or it happens that sometimes you can relate, sometimes you cannot?
So at the practical level, for completely massless amplitudes, it's fully understood at tree level, at lowest order. And it's proven. And then if you go to loop level, then it's understood for the integrands. It's not, I would say, completely proven, but it's applicable as a computational technology. Allows you to reorganize the computation, vastly simplify the computation of the integrand, which you then have to feed through Feynman integrals. So that's at kind of the practical level. At a deeper level, I would say it's not really understood. There's clearly some mathematical structure. So there are, for example, for classical solutions, there are some classical solutions in GR that you can relate to essentially double copies of Yang-Mills or Coulomb solutions. But in general, it's not really understood. This is something which is completely unobvious at the level of the Lagrangian or the Hamiltonian. So yes, there's clearly some deeper mathematical structure which is still waiting to be uncovered.
I mean, at the loop level, you need to renormalize it.
So first of all, in the applications to supergravity and in the applications to classical physics, that's not an issue. You don't need to do that. But if you were doing, for example, if you're trying to do a one-loop computation of, let's say, the quantum corrections to the potential in GR, then it just, I mean, GR, has at low energy has an infinite tower of operators, and you just have to absorb that infinity into one of those operators. It's something that's well understood how to do in effective field theory. So there's nothing particularly radical or novel about that aspect.
Any other questions?
So just curiosity. So you said that the 5-jet is sort of like the state of the art in computation of amplitude.
So actually, the 5 partons. So there's 2 incoming and 3 outgoing. And that's if we're looking at next to leading order. At next to leading order, so for precision physics, let's say 3% precision, then yes, 3 jets is kind of the frontier. But if you're accepting like a 10 to 15%, then you can basically go out to as many jets as you're willing to throw computer power at.
So I wanted to ask just if you could in a sentence or two. So how do I go from some perturbative QCD computation to what they actually, so maybe they're PDE, PDF, I mean, so how far it is from what they actually measure?
So there's a lot of technology that, of course, I don't have time to cover, but there's many ingredients. So in a sense, you have to understand the probability of finding the initial state inside the proton. Those are things that are called parton distribution functions, and those ultimately have to be fitted from data, but their evolution, again, is governed by perturbative QCD. And then because it's a theory that involves massless particles, they're infrared divergence. It's kind of inevitable when you're doing perturbation theory organized in terms of states with fixed particle. And actually, a lot of the technical challenge of the actual computation beyond computing the loop amplitudes is precisely organizing those infrared divergences and canceling. And it's also that separation is also a source of let's say, the numerical difficulty in making these predictions. So what has to happen is that there are some contributions where you're integrating, for example, you square the loop momentum and you integrate it. And there are other contributions where you're integrating a lower a lower loop amplitude, for example, a tree amplitude, but you're integrating it in regions where some of the gluons are becoming soft, for example. Soft, and therefore they don't produce an observable jet. And then in order to do the comparison between the perturbation theory and the detector, so the detector, of course, is measuring hadrons. The perturbation theory is, in a certain sense, measuring partons. So you can think of the perturbation theory as doing things with a detector that's much smaller than the size of the proton. And so then you just have to make sure that the quantities that you're measuring in the real detector and in your theoretical detector are compatible. There's a whole formalism for understanding what observables and how you connect the two. But jets are one of the observables that you can connect. I mean, you essentially would measure jets at the parton level and compare them with jets at the hadron level. And there are corrections, but if it's done properly, those corrections are smaller than the perturbative ones.
Any more questions? There are no further questions, then let's thank the speaker again.